So it's 11 o'clock. Dear Professor Ramanathan, representatives from the Crafoord Foundation, colleagues and friends, welcome to the Crafoord Prize Lecture in Geosciences. My name is Persson, and I've had the honor and pleasure of serving as chair of the prize committee for the Crafoord Prize in Geosciences. Before I give the floor to my colleague, Professor Örjan Gustafsson, who will introduce this year's laureate, I would like to provide some background on why we are gathered here today. That is the origins of the Crafoord Foundation and the Crafoord Prize. All of this can be traced back to one man, Holger Crafoord. He was born in Stockholm in 1908, raised by his mother, Hanna. He excelled early academically, first at Östra Real and later at the Stockholm School of Economics. And there his talent caught the attention of Ruben Rausing, the founder of the packaging company Åkerlund and Rausing, who recruited the 22-year-old Crafoord to Lund. Just over a decade later, Holger Crafoord became the CEO of the company, and his partnership with Ruben Rausing proved transformative in many ways, ultimately leading to the creation of the Tetra Pak, a company, I guess it's familiar to many of us. In the early 1960s, Holger Crafoord and Professor Nils Alvall met, and Holger learned about Nils Alvall's invention of the artificial kidney. Crafoord financed the development of this technology from his own pocket, and in 1964 started the company Gambro. 4 years later, the world saw the introduction of the first working dialysis machine by Gambro. At the end of his life, Holger Crafoord suffered from severe arthritis. He passed away in 1982, but a few years before his death, he, together with his wife, Anna-Greta, established the Crafoord Foundation, a testament to his commitment to scientific research and societal progress. The foundation has since grown almost exponentially and has distributed over 2.5 billion Swedish kronor to support scientific research, humanitarian efforts, and initiatives for children and individuals with disabilities. Holger's vision was a foundation that would not only support excellent and groundbreaking research, but also improve lives in meaningful ways. The connection between groundbreaking research and improving living conditions has several parallels to this year's laureate, Professor Ramanathan, as you will hear soon later. Now to the reason why we're here today, the Crafoord Prize. It was established in 1980 by Holger Crafoord and is awarded in partnership with the Royal Swedish Academy of Sciences. And today, with a prize sum of 8 million Swedish kronor, it ranks among the largest and most prestigious scientific prizes in the world. The Crafoord Prize recognizes outstanding achievements in mathematics, astronomy, geosciences, biosciences, and polyarthritis. In a way, you can view this as the Nobel Prize cousins, specializing in areas that the Nobel Prize doesn't cover. It's impossible to do justice to the work of Holger Crafoord and the impact of the Crafoord Foundation in just a few minutes. However, I hope with this brief overview conveys the legacy is not only of industrial success, but also of profound generosity and vision. And with that, I would like to give the word to Örjan Gustafsson, who will introduce the Crafoord Prize laureate, Professor Ramanathan. Please, Örjan.
Good morning, everyone. It is my deep honor and joy to share with you a brief introduction of the 2026 Crafoord Prize Laureate in Geosciences, Veerabhadran Ramanathan. He receives the prize for fundamental contributions to our understanding of how aerosol particles and other climate pollutants influence the atmospheric energy balance and the Earth system. So the prize goes to climate science, and specifically the science of climate change. So who is Ramanathan and what is the science that he has achieved? I can only give small tidbits of that. Ram was born in 1944 in Chennai, educated in India, the Indian Institute of Science in Bangalore. So you see on top here, he's now for a long time been a distinguished professor of atmospheric and climate sciences at the Scripps Institute of Oceanography, University of California, San Diego, in La Jolla. Beautiful La Jolla. He's an elected member of numerous academies, including the US National Academy of Sciences, the Pontifical Academy of Sciences, and the Royal Swedish Academy of Sciences. He has been receiving many accolades, including the Tyler Prize, the Tang Prize, the Blue Planet Prize, the Volvo Environment Prize. He's been declared an Earth Hero of the United Nations. And last year he received the Grand Medal of the French Academy. He started out his career as a NASA scientist. He was one of the key masterminds behind the Erbe satellite missions, which I believe Ram will tell us a little bit more about in his presentation that follows. He was also associated for some time with the very important National Center of Atmospheric Research, NCAR, in Colorado. And now he has for decades had as a base University of California, San Diego, and Scripps Institute of Oceanography. I'm going to share with you about one slide each on three of his diverse contributions. He's a little bit of a Da Vinci type scientist that's contributed in many different areas of climate science. He made fundamental findings on Earth radiation and the role of aerosols and clouds. He discovered that synthetic chemicals like chlorofluorocarbons and their replacement products that deplete the stratospheric ozone layer also are super strong greenhouse gases. And he made that impact on also the policy of those chemicals. He has also been a key person behind the concept of non-CO2 short-lived climate pollutants. I think many of us think also of Ram as a bridge builder and a convener for science for policy, and for climate literacy. So he came to NASA as a young scientist. See the picture to the right there of somewhat younger Ram, the one with the crown on his head. He somehow was able to convince NASA to put interferometers and other type of instruments on satellites to make direct observations on how solar and thermal radiation interact with greenhouse gases and aerosols. This led to actually the first quantitative measurements of the Earth's greenhouse effect. And also quantitatively proved that clouds had a net global cooling effect. I believe Ram will share more on that. Sort of on the side, I really need to find out from Ramanathan how this happened. But he sat in his office in the top right here, thinking and calculating, and somehow realized that these tropospheric ozone depleting chemicals, CFCs and HCFCs and so on, also are very strong greenhouse gases. To the tune, the replacement products now hydrofluorocarbons that doesn't appreciably deplete the tropospheric ozone layer. They have a greenhouse warming potential 15,000 times that of carbon dioxide per molecule. So very strong greenhouse gases. Then he teamed up with David Selke, a policy expert, and for decades were communicating about that, which eventually science-based led to the amendment of the Montreal Protocol, the Kigali Amendment, recognizing the greenhouse warming potential of these chemicals. And phasing out those by itself shaves off 0.3 degrees Celsius warming. Third, and finally, the one I'm going to talk about, the science of Ramanathan here as an introduction. The focus turned to the nexus of air pollution and climate change. Ramanathan, together with Nobel Prize winner Paul Crutzen, Jos Lelleveld, A.P. Mitra from India, our own Henning Rode, who is here, convened this Indian Ocean experiment to study the connection between air pollution and climate change. Up to that point, we had pretty much thought about air pollution as an urban phenomenon. But they proved that this air pollution spreads over regional scale, over South Asia and neighboring oceans, and had impact on the climate. Very important finding. The follow-up to the INDEX program was the atmospheric brown clouds program, where we recognize we need permanent installment to continuously measure and research these phenomena. So the atmospheric brown cloud established strategically located receptor observatories. That has transformed into what is today called the South Asian Pollution Experiment that carries on this legacy with more than 20 years of measurements with lots of findings. Some of the key findings of the INDO-X led by Raman was that this urban-like air pollution spreads over a regional scale and have an impact on climate. The finding that soot and black carbon particles played an important role, together with other aerosols and gases. They were non-CO2. And the concept of short-lived climate pollutants was born. SLCPs now has its own chapter in IPCC reports and as provisions for emission reduction under the United Nations Climate Treaty. It's wider, the impact is wider than this. Science for Ramanathan seems to always be driven towards a benefit society through policy actions and other means. He has contributed instrumentally in this area. He has a fantastic convening power. He also has very strong convincing power. And here you see to the bottom right, he has been convincing 3 popes, including Pope Francis, who he had a close relationship with, to engage fully in this fight for protecting our common home for the better of people and the planet. And also several governors of California and elsewhere, and there's a photo of Ram with Governor Brown of California. Growing up in India, I feel Ramanathan has always had a special eye to the 3 billion poorest on Earth, the most vulnerable to climate change, and also a special eye to younger scientists and young researchers, not so young researchers. But many of us has benefited from Ramanathan including us in his circles. And one example, he has built a program called Climate Change Solutions, Bending the Curve, educational package that we also teach at Stockholm University and elsewhere, with the goal to raise 1 million climate champions. And with that, I'd like to introduce one climate champion, the 2026 Crafoord Prize Laureate Ramanathan. And the floor is yours, or the chair is yours.
Thank you. Thank you, Professor Gustafsson, and a lot of my colleagues here. I'm truly very, very deeply honored by this recognition. I want to give my sincere thanks to the Crafoord Foundation, the Royal Society, the Royal Swedish Academy of Sciences, and the Crafoord Committee, which chose me as this year's laureate. I was very pleased to meet the Crafoord family. Thank you very much. This is going to have a huge impact on what I'm planning to do with climate change. these are, challenging times for climate scientists like me who have been working on this problem for decades. This is my 56th year in climate change science. We have witnessed our predictions made in the 1980s, 1990s coming true. I personally would have preferred that my predictions did not come true. They were dire predictions. But the gigantic efforts which were started by scientists, United Nations, and many nations to stop the crises have not succeeded so far. The emissions are still going up. And however, I'm confident success is still within our reach. But we need a new approach. And I want to reassure the Crafoord Committee and the family and the foundations here that I'm going to use this recognition given by this prize and the financial part to do my best to point us in the right direction to solve the climate change. So what I'm going to do today is talk to you about the science of climate change. This is being, the public mistrust in science is growing in certain countries. I want to show you we have a robust theory of climate change based on sound fundamental physical principles, and more importantly, it has passed crucial tests. My own work was devoted to testing this theory again and again and again. And I'll detail this test for you. I'm going to refer to this theory as the energy balance theory of climate change. This is the first time I'm using that phrase. And I want to thank the Crafoord Committee. I have received numerous awards. This is the first award which mentions energy balance. And that is the crux of my work on energy balance. And I'll tell you what it is. So using this theory, I'll show you that the climate system is predictable on a 1 to 2 decade time scale. That is, the theory is robust enough that I can predict what's going to happen in the next 10 to 15 years. And I have made a series of about 4 predictions. I'm going to conclude my talk with somewhat of a dire scientific prediction, for the next 15 years. This will be my 4th, and I'm thinking my last prediction. After all, I'm 81 years old. And I've been making predictions every 10, 15 years, so you can add the time period. And but that predictability is the hope we have, meaning we still have time to address this issue, protect the people and the ecosystem. And what I want to mention to you is the warming has been accelerating rapidly in the last 15 years. Many scientists, including Professor Gunnar, who is here, or he'll be coming to Stockholm, made some insights into that. And what all this tells me is that while the efforts being done are tremendous, we need a new approach. They're not working. Okay, we need a new approach. And through the Pontifical Academy of Sciences, we report directly to the Holy Father, the Pope, and Professor Gustafsson is also a member of this academy. We are advancing a global movement for this new approach. I'll conclude with that. So let me start with my first slide. This was a picture of a beautiful planet taken from the backside of the moon just 2 months ago, 6 weeks ago, by the Artemis crew. When I saw that picture, I was reminded of what my astronomer friends tell. They call Earth as the Goldilocks planet. Our inner planet, Venus, is too close to the sun. It's 400 degrees Celsius hot. Mars is too far away. It's minus 50 degrees cold. the Earth is the only thing right temperature. And they said because we are the right distance from the sun. I will show you it took a lot more than that for the planet to have that Goldilocks planet. Remember, Goldilocks is a fictional character. She likes to have her porridge at exactly the right temperature. Okay? So the question which came to me was, how long are we going to be the Goldilocks planet? So let me start with my approach. Remember, I said that I'm going to be testing this theory. And I followed a framework right from the day one when I got into this field in 1970. Detection, attribution, and prediction. Okay? You detect a change, then you use your scientific knowledge to attribute that change to some cause, forcing, you can call it. And between the two of them, you then develop a theory, or if the theory is already there, you improve it and test the theory by making prediction. All right, so that's the framework I followed. I'm going to walk you through this. And so what I'm showing on the left-hand side is the temperature of the planet averaged over the entire globe, from Antarctic to Arctic. Every corner of the Earth has been measured and averaged. And the data from 1850 to 1900s, they may have larger uncertainty because we didn't have enough observing systems. Starting from 1980s, we had satellites covering missing gaps. So you see that the planet's temperature is starting to warm around 1900, and then it took a pause around 1950 to 1980, and then it took off 1985, and it's been going up and up. And the last 15 years, it's taking off on a new trajectory, and I'm going to talk to you about that. The right side is taking the temperature of last year for the entire planet and comparing that what happened in the middle of the 20th century. What you see here is that the land is getting hotter than the ocean. The northern hemisphere is getting hotter than the southern hemisphere. And then you see that the Arctic and the antipolar regions are warming a lot more. All of these were predicted in the 1970s, okay, by this theory. And I'll walk you through that. So the question, I call the right side as the asymmetric warming. The land is warming more, the Arctic is warming more, so it's asymmetry. So it looks complex, but that complexity was predicted, okay? So let me walk you through one by one. So that was detection. I don't think anyone doubts or can doubt that the planet is heating up. Now the question, what is the attribution? This is a measurement made by a colleague of mine. He passed away, David Keeling at Scripps Institute of Oceanography, the seminal measurement which launched the climate change in a legitimate way. Carbon dioxide concentration going up and up and up. So what is carbon dioxide? Remember, when you burn fuel, fuel is hydrocarbon, hydrogen and carbon. When you burn it, the carbon gets attached to the oxygen in the air, becomes carbon dioxide, okay? The insidious thing about this is that once you release it, 50% stays for 100 years, a century or more, and 20% for 1,000 years, okay? What happens to it? Let me show this. Most of my work was really using observations. I have many personalities. Some of my colleagues think I am a modeler, some think I'm an experimentalist. I am all of the above. And in India, I built India's first Mach-Zehnder interferometer as a graduate student. So my origin is experimental science. But for 4 years, I took time off from observations and built this climate model. Why? Because remember, you detect the change, then you attribute it to some cause, but you need a model and a theory to test that. Okay, so that's why all three were needed. Let's see what happens. I'm still sitting in San Diego, and we are now in Sweden. Sweden is on the top left corner. And I'm going to show you air motions around 5 kilometers from the surface, okay? So and the clock is ticking on the left-hand side. If you're sitting on Eastern Asia, that air comes to me within 5 to 10 days in San Diego. I design unmanned aircraft drones to monitor this. I know it not only from my model, from real data. And the CO2 I emit goes to New York City within 2 to 3 days. And New York City sends their gift to Europe in less than 6 days. Okay, so what does it tell you? That emission anywhere in the planet is global warming everywhere. Okay? And so what happens to the CO2 no matter where you emit it? In America or Sweden or China or India, it covers the entire planet like a blanket. All right? So how does a blanket keep you warm on a cold winter night? The blanket doesn't give you any heat. It just traps your body heat. That's exactly how the CO2 blanket works. It traps the heat coming from infrared heat coming from the Earth. We used to call it greenhouse effect. I used to call it too, but it's a misnomer. So I'm changing it to blanket effect. Many have caught on to it, and I don't have time to delve into why greenhouse effect is not a correct name. But the key message I want you to take home is that we are never ever going to solve this problem by saying China is emitting it, India is emitting it, Germany is emitting it. No, we are all in this together. We have to work together on this problem at least. Okay. So where is my origin, and where I grew up biases quite a bit of my work in the later years. I tell my students always, it's okay to have a bias, but declare it. Everyone knows what your bias is. So my heart and soul is with the poor. This is the home next to my grandfather's home. I went there when I was with my wife for my 60th birthday. I used to spend my years from 5 to 13, summertime here. That's exactly how I was, a topless kid, sitting in the veranda the whole day. Why veranda? There were no electricity, no fans. Inside was too hot. And they won't buy young kids footwear because it's too expensive. Everyone had 6 kids, imagining buying 6 pairs of sandals every year. So we were barefoot. We couldn't touch the ground. The only place is that veranda. Okay? What I was shocked to find, that was in 1950, I was on that veranda. I'm going there 50 years later, still that's the only fun place to be. And imagine heating up that place. Imagine taking away droughts. There are 3 billion people in similar situation. This is what I advise Pope Francis. 50 to 60% of the emission comes from the wealthiest 1 billion, from me and my companions. The emissions of this bottom 3 billion, I'm calling it bottom not in a derogatory sense, they are bottom of the energy pyramid. We are all on top of the pyramid, they're on the bottom. Their emission is less than 10%. And we have lost $3.6 trillion in the last 25 years due to weather extremes. They suffered 75% of it. Just imagine that. So somehow this topless kid found himself working at NASA. And the series of accidents propelled me there. That's the reason for the title, Accidental Scientist. And it so happened, my whole life was, whatever good things happened to me was all series of lucky accidents. I was hired by NASA to look at how the rocket emissions was influencing climate and ozone layer. But it so happened my next door office mate was the most brilliant engineer, George Sweet. He wanted to launch a climate satellite, and I found my buddy and partner. So I told him how to measure, what to measure. So we designed this Earth radiation budget satellite. When I say we designed, I just told him what to measure. He did how to measure it. And the main thing we did was, for the first time it was done, we had calibration. So most satellite instruments were not calibrated, so you can't use them to look at change. So this instrument is continuing to this day. This satellite, it's sons of Urbi or daughters of Urbi. And I'm going to, that's what is showing shocking information of what the planet is changing. Okay, so this was launched in 1984, Space Shuttle Challenger, and the astronauts there was Kathy Sullivan and Sally Ride. They launched it. Sally then joined Scripps into Oceanography, and she recruited me back 10 years later. Anyhow, so I'm going to talk to you about this energy budget, what we learned from the satellite. But as you know, the Challenger had a disastrous experience, and a few years later it just crashed. Astronauts died. I fortunately had a safe landing. This was 2004, when I turned 60. I was sitting in the middle of the Indian Ocean launching drones. And I get this letter from the Vatican that Pope John Paul II admitted me to the Vatican Science Academy. What I found remarkable is that it's international in scope, multiracial in composition. They don't check your race. I didn't know all this. Now I'm a council member. I'm involved in electing members. We never ask the person's race, not even religion. I'm not a Catholic and I'm not even a Christian, but still I'm a council member. It's a remarkable science academy. We can talk about any topics in the sun. I found there science and faith can get together to address the climate change problem, because people listen to religious leaders than people like me, right? They have more access. Anyhow, so now that's the background. So let me just tell you what the theory of climate and climate change is. You see on the satellite, there are three things which drive the climate of the planet. The incoming sunlight, okay? Not all of the sunlight is absorbed by the planet. Some is reflected back. In the 70s, we didn't know how much. And then the rest goes to heat the planet. Okay, we know that. Just go outside, you feel warm. The sun is heating you, and it's heating the rest of the planet. When it heats you, you give off more energy as infrared radiation. Every person emits this. And so the planet heats up. It gives off this heat as heat radiation, infrared radiation. This process goes on until what comes in is balanced by what goes out. Okay, it's amazing, amazing thing. So I call it Earth energy balance equals S incoming sunlight minus SR, which is reflected sunlight, minus emitted sunlight. Okay? I still can't believe this equation is able to explain what's happening with the climate system. Remember, climate system, incredibly complex. Your trees, your oceans, your house, everything influences. Still, these three parameters can catch it, okay? And I didn't believe this, that's why I got into the Urbi satellite and I wanted to test it. The thing, what's happening now is that we threw the CO2 in the air, we just covered it like a blanket, and the blanket traps the heat coming from your body and from the earth, so the EIR, energy going out, has come down, decreased. So the EEB has become sort of zero positive. There's more heating in the planet, and the planet has to heat up. Then it'll increase the emission and restores the balance. So I wanted to know how much was being trapped and how is the planet responding to it. Okay? And the bottom is the equation for determining the temperature. I think I see some students and postdocs. I'm going to give you a quiz on this equation, so hopefully you'll remember it. Don't take me seriously, it was just a joke. All right. Now, so that's the satellite we built, okay? And you see on the bottom instruments sticking out. They are just scanning the Earth. And the top one is the, capturing the solar energy for powering these instruments. And how did we do the calibration? We had inside a black body source, energy source, giving radiation. The instrument will measure it and know that it's not drifting. And then we will turn the satellite belly up, look at the moon, assume the moon's temperature is not changing, okay? So what I'll show you is that how did I use these measurements? When I say I'm talking about I had tremendous amount of gifted students and postdocs in my lab. And all of them contributed to this. So let me walk you through this. How is the planet's climate maintained? So what I'm going to do, what maintains this Goldilocks planet? It's just not the distance from the sun. Okay, that's 6 other things controlling. Then what we are doing to it, and how is it responding? So the first thing we measured is how much was coming in. So I call it 100%. The units 340 watts per square meter. Just to give you a framework, not that you need to remember this, the watts, the W is the same as, we say 60-watt light bulb, 100-watt light bulb, source of energy. Per meter squared, per square meter of the Earth's surface. So our instrument resolution was 50 kilometers. So we measured every 50 kilometers throughout the planet, okay? And about twice a day, we go around the Earth. So based on that, so we found the planet was reflecting 30% back to space. It was not used. We call it albedo. Okay? Mainly clouds, ice sheets, trees, oceans, everything is reflecting. So 70% comes in, and the Earth heats up and gives off this energy in the infrared wavelengths as heat energy. So we determined the balance. I must tell you, our instrument, we didn't get an exact balance. We are off by plus or minus 1%, but that's the uncertainty of the instruments. Okay? Next. Normally people, when I say CO2 greenhouse effect, we think it's just the pollution which is causing the greenhouse effect. No. There is a natural blanket. Okay? I wanted to measure the thickness of that natural blanket. So when I say thickness, I think in terms of energy. I'm an energy guy. So I think in terms of watts. Okay, so when I say thickness, think in terms of heat trapped. So using the ocean temperature, we measured what's coming from the ocean, the whole global oceans. That's about 400 watts per meter squared. But what gets out is only 268. Okay? What happened to the rest? Natural blanket. What is that natural blanket? Water vapor. Water vapor is the dominant greenhouse gas or heat trapping. Okay? So it trapped about 131 watts. 30% of what was emitted couldn't go out. If Mother Nature didn't give us water vapor, this planet would be frozen. So we are a Goldilocks planet, not just because we are at the right distance from the sun. We have the oceans and the water vapor. Okay? I'll come to this. A famous Swedish scientist, Svante Arrhenius, made a remarkable prediction. I got to him thinking, I'm going to prove him wrong and get famous on that. It turned out he was so close to being correct. And I'll talk to you about it. It deals with the water vapor, right? So the next major regulator of the climate is clouds. You know that, right? On a midsummer time, when you have overhead clouds, it gets cooler because the clouds bounce off the sunlight. But on a nighttime, a cloudy sky is warmer. Why is that? The clouds are also a blanket. So they were kind of schizophrenic. On the one hand, they will heat the planet by trapping heat. On the other hand, they reflect sunlight cool. We didn't know what was the net effect. All we had was models. And what NASA scientists were doing was trying to measure every cloud. That's impossible. Clouds are turbulent. No characteristic length scale. Remember what Einstein said when they asked him, he said, are you afraid to die? He said, yes. When this journalist got all excited, so they got something Einstein is scared of. They asked him why. He said, I'm afraid to find out even God doesn't understand turbulence. And I told this to NASA scientists. And what I came up with was a very simple, in fact, the simplest way to look at clouds. Don't look at clouds because they don't have a character scale. So look at clear skies. Find out what's coming out. And then look at the cloudy sky, cloud plus clear, and subtract the two to get the clouds effect. It's called twin planet, is what I call it. And there was a vote. I won by just one vote. And thanks to that, that too, because when they took the vote, my second son was born that day. So one committee member took pity with me. Oh, he has a newborn baby. Let's not disappoint him. It turned out that's the only measurements we now have to solve a critical problem, the twin planet Earth. So what we found doing this twin planet method, on the left-hand side, you see the blanket effect. On the right-hand side, you see the albedo effect. Look at the tropics, which has the most thickest, deepest clouds. They reflect enormous amount of sunlight, but they were also trapping enormous amount of heat, infrared. When you add the two, see the bottom slide, the tropics looks like it has no clouds, as far as energy budget is concerned. And the clouds were cooling the climate. Okay, the blanket effect was 30. The albedo effect was minus 48. When you add the two, the net effect was minus 18, but they were all coming from middle altitude clouds. The one you take off from Sweden, the entire Atlantic, you see a white sheet. That's what's cooling it. Okay? And then the stratocumulus clouds, you can see off of the west coast of continents. I want to tell you about this. How lucky we are. We have a Goldilocks planet. If that albedo effect, instead of being 48, say it was 54, just 6 watts difference, the planet would be frozen, including India, everywhere. On the other hand, if that blanket effect instead of 30, it was 36, it'll be way too hot, at least 5 to 6 degrees too hot. So that's how delicate we are. And when I have sleepless nights, it's on this. Oh, what happens if the clouds decide to change? It's turbulent. I can't even ask God because Einstein told me even God doesn't understand turbulence. So that's the issue. We are tampering with the planet which we have not completely understood. It could go chaotic. So far it has behaved linearly. So that's as far as what's maintaining the present climate. Now let me talk about, I moved to climate change. Örjan said, how did I get into this? I said, 75, I said, NASA. My daytime job was to look at the rocket effects. So I did all this work in the night times, evening and night. I was just married my wife who's here a year ago, 74. So I don't know how she put up with me. I used to come home, start working with my calculator. And but she became a great partner in my science. The reason I started CFCs, the year before that, 1974, Roland and Molina published a paper for which they got the Nobel Prize with Paul Crutzen. The CFCs were destroying the ozone layer. I had an engineer's job in India. My job was to prevent the CFCs from escaping your refrigerators. They would leak away. So it struck things. I got into the quantum mechanics of CFCs. I was shocked to find each ton of CFCs will have the same effect as 10,000 tons of carbon dioxide. Suddenly, we created a new field where chemistry became an important part of climate change. Before meteorologists studied climate change or just do the meteorology, no. Chemistry became an integral part because CFCs was destroying the ozone layer and the ozone layer was impacting climate, became a complex issue. I'm going to skip this. Some of this physics of this is intricate. I'm going to talk about it in Stockholm. So that was my first prediction. It took scientists about 10 years. They initially thought it was crazy. It was this, it was that. But finally, they were convinced CFCs was legitimate. So suddenly the problem became twice as important. It is just not carbon dioxide alone, it's carbon dioxide plus CFC, the whole host of gases were thrown in. So I got curious and I said, okay, if the problem is twice as important, I should see the warming now. If I don't see the warming now, when am I going to see it? Okay, it's what called statistical dynamical work. That is, there is noise. You see the temperature, how it goes up and down, that's noise. Where is that noise coming from? Weather. One year is not the same as the other, right? So the question was, when are you going to see the warming beyond the noise? I teamed up with the famous meteorologist Ramanathan. There is a name for a Madden-Julian oscillation of waves. So we predicted that if the theory is correct, and using the Earth energy balance theory, just those three parameters, we predicted the warming should show up by the year 2000, if not before. So if you look at the temperature record, that's it, around 1995 is when the temperature shot up above the background noise. Okay. So the second of my prediction came true. It took about 15 years. Remember I told you predictability is 10 to 20 years? Keep that in mind. Okay. What happened was the warming was not as much as we predicted. All right? It was a lot smaller. So my first suspicion was, oh, the theory is exaggerating. But around this time, some well-known chemists and a pioneer here, Professor Henning Ruther, they were working on air pollution because they were concerned about acid rain. And it turned out the air pollution, you all know, when the air pollution is there, it's hazy. Sky is hazy, right? Why is it hazy? Because it's scattering sunlight. And it's scattering sunlight towards you, but also back to space. So then they were suggesting this air pollution haze was masking some of the warmth. They didn't use the word masking. I coined that term, mask. And so what we were having was we threw up this carbon dioxide gas, CFCs, to create a blanket. There's a natural blanket. We made the blanket thicker. And then on top of the blanket, we are throwing mirrors, this haze, reflecting sunlight, and it has covered some of the greenhouse gas effect. So I teamed up with Paul Crutzen, in many ways, my mentor in bringing in chemistry, and a great friend and a great colleague of mine. And Mitra, he was an Indian science leader, and Professor Jos Lelyfeld, he's at the Max Planck chemist. We mounted this massive experiment. Over 200 scientists joined. India joined. So we had 2 ships. Okay. I'm way behind time. All right. Let me. So we had all kinds of instruments to measure how much sunlight was being reflected. And we see here on the top, on the bottom, I have my satellite looking directly at the Indian Ocean. And we see that on the bottom, we had this aerosol particles going up, and we see the sunlight going down, decreasing minus. So we measured the mask. We sort of convinced ourselves, yes, the aerosols are masking. I'm going to skip some of these, and this shows these clouds were everywhere, this aerosol pollution. It's just not India, it's everywhere. And then we formed a project, Atmospheric Brown Clouds, Professor Henning Rode and myself sort of co-chaired it. So this is the summary, okay, of what's happening. The carbon dioxide has trapped about 2 watts per meter squared as a blanket, and all the other gases 1.7, and the mask. There were 2 things in the mask. One was reflecting particles, sulfates, nitrates. It also had black carbon. And when you add all the 2, the net effect, the mask was to cut down about 40% of the blanket effect. All right? And so the deduction from this, without the mask, the planet should have heated already close to 2 degrees. Okay? It's the mask which has kept us. And the vexing part of that is this air pollution mask is killing millions every year. So we need to get rid of it. Okay? And the next thing, now I've finished as far as how we are changing the planet and how is the planet responding. And the responding part comes, the vapor pressure, as the planet is heating up. Look at the pan of water I have. When you heat it, just do this experiment. Put a pan of water and turn your burner on, it'll disappear. Where is the water going? It is taking the energy from the burner and become vapor. And this is what Svante Arrhenius said. When you heat the planet, the water vapor will go up and it'll amplify the warming. And we made these measurements, and you see I was shocked. It was falling almost linearly everywhere in the ocean. We collected the data. And the slope matches that equation, which is the basic laws of thermodynamics. It's called Clausius-Clapeyron equation. Okay? So it says the water vapor will increase by about 6% for every degree warming. The blanket is getting. See, remember you're putting the CO2 and CFCs. The blanket traps the heat, so the planet gets warmer to get rid of the heat. But when it gets warmer, it throws up this water vapor blanket. Okay? Amplifying. And honestly, of all the things I've shown, this was my most important finding. No one is aware of this. It's a well-kept secret. What we are showing is that the H2O feedback, and so we measured the greenhouse effect. Remember, from the space, and I plotted that, and it sees how it's increasing at the rate of about 3.53. It's trapping more. So when you heat the planet, the surface of the ocean radiating 5.5 watts to get rid of the heat. But 3.5 is trapped by the water vapor. So only 2 watts escapes. Okay? If that water vapor feedback was not there, I don't think you would have given me this award, because the climate problem wouldn't have been that important. The whole warming would have been only 0.5 degree. Okay? And I'm shocked you gave the Nobel Prize and the Crafoord Prize to Suki Manabe. He was the only one who got that. His model showed that. I didn't trust any models. He got very similar to 3.5. And that's what I mean. We have a powerful theory, and the models are supporting it. Okay? Same feedback happens with the ice. Polar ice here off of Scandinavia places are retreating. In fact, Professor Örjan Gustafsson is studying this issue. And we captured that. We found that was also amplifying the feedback. The planet is getting darker and darker and darker. Okay? I was going to explain, I think I'll do it at Stockholm. This basically captures the key numbers which came out of my 55 years of work. Starting from the left side is what the blanket is trapping, And the middle is what the humans are doing to that blanket. And the right part was how is the system responding. The system is working hard to get to see the 4 watts. The ocean is radiating, but the water vapor blanket is trapping it. And by the time you all add all these feedbacks, only 2 watts can escape. That's why the warming is as severe. We made a prediction that we will reach 1.5 degree warming 18 years, 2018. And you see this temperature records. It's really accelerating. It's already reached 1.5, very close to our predictions. So sadly, one after another, all our predictions, using just the simple theory of 3 parameters, okay? And I'm going to skip some of this. One thing I want to touch on you is that, which is being missed by most of my colleagues, what is the connection between warming and weather extremes? It's just not the temperature. When you increase the temperature, the water vapor goes up. It has latent energy. Remember that it was water in the ocean, took the energy, and then releases it. So when you look at the thermodynamic energy, the actual warming in the tropics is 3 times more, 2.5 degrees warming in terms of that unit. And that's what kicking up the storms. Okay? And unfortunately, the 3 billion live in that. That's why they're losing so much in the tropics. So I want to conclude with 2 things. The theory of climate has passed critical tests. The deduction is that theory is based on fundamental principles. The Clausius-Clapeyron equation, others hold a death grip on the planet that I don't see any way of escaping it. Okay? So I want to conclude with 3 things. So you ask, there is a Gordian knot. I told you we have a theory, it explains everything, but there is one thing, unsolved problem, which could be our real Gordian knot. If you ask me, is the warmer planet less or more cloudy? I don't know the answer to that question. Why is that important? Remember I showed you the albedo effect, the blanket effect, just 2% off. It'll take off, okay? And fortunately, if I look at the data we created, the clouds are not changing much. They are in the linear regime. I told you my prediction is that we are going to hit 2 degree warming, which we have not seen in the last few million years, in about 18 years, but 2041 to 2045, that's my prediction. If it goes into the nonlinear regime, then I don't know. Whether it's, once the climate goes in nonlinear regime, I can't trust any models. Okay? So we have to live through it. So we are saying that's why we need a new approach. In the Pontifical Academy of Sciences, Professor Gustafsson is part of this. We are saying we need to build resilience to people. Okay? That resilience, you see, I was advising Pope Francis about the 3 billion in his encyclical. He came with a beautiful sentence. It makes me emotional every time I read it. He said, cry of the earth should be heard with the cry of the poor. Okay? And the mast is mitigation to reduce the risk. Right now we are spending 95% of efforts only on the M, mitigation, and we have not succeeded. We are saying we have to adapt. We have to spend equal amount on adaptation. That involves human beings, your infrastructure, everything. None of them, in any country is ready for this. And societal transformation. And there has to be collective behavioral transformation. If you give me 30 seconds more, I'll finish this. So, this is the accident of scientists, series of accidents which made my life what it is. I'm not going to talk about this. I'll read the thank you note. Kindly note my top thanks is to my wife and soulmate, without whose support there is no way I could have done any of this. So, and of course, numerous colleagues. Let me conclude with this. Remember what I showed. Emissions anywhere is global warming everywhere. So please don't point fingers, even at fossil fuels. Without fossil fuels, I couldn't have come to this country or to US. It benefited all of us, but it's outdated. We are all interconnected. Everything and everyone on the planet is interconnected. We have to solve this problem together. We cannot solve it by pointing fingers. The encouraging factor is there is time. The second thing is we know how to solve the problem. It's not something we don't know. We know how to solve the problem. And we know how to create a sustainable future. In fact, the Stockholm Resilience Center here and Professor Jan Rockström, they're playing pioneering roles. We also have the brain power, the technology, and the socials for quick action. But we need a new approach. We can't just say mitigation. We're going to let so many people suffer. We need the must. We need the adaptation. We need societal transformation. I hope I have provided sufficient data on scientific verification to demonstrate that we scientists collectively, just not me, understand the climate system well enough to suggest this. My fervent hope is that this knowledge warrants a top-to-bottom society-wide effort to chart a new course for protecting people and ecosystems from human intervention. And I want to give my assurance to the Crafoord family and the foundation. I will be using this prize, the recognition it gives, to push us towards sustainable living. Thank you.